Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 60th Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 60 is prime pair sets. The primes 3, 7, 109, and 673 are quite remarkable. By taking any two of those and concatenating them in any order, the result will always be prime. For example, taking 7 and 109, both 7109 and 1097 are prime. The sum of these four primes, 792, represents the lowest sum for a set of four primes with this property. Find the lowest sum for a set of 5 primes for which any two primes concatenate to produce another prime. Okay, so I've actually spent quite a lot of time on this already. I have some code here. And I'm going to go ahead and just sort of start over. So we start with our problem statement, and obviously I'm copying and pasting some code here, but okay, so let's go ahead and solve this for 4 primes first. So because I've worked on this quite a lot already, and gotten the wrong answer, and then tried again and gotten, I'm not going to say the wrong answer, but it didn't go through. I let it run for over an hour and it didn't work, and our time limit is 1 minute. So instead, we're just going to go ahead and start all over here. So first step, find first million primes. And actually, I'm going to change... No, I'm going to leave that the same. And what I'm going to do is use the sieve method that has worked before. Or find not first million primes, but actually all primes under 1 million. There we go. That'll do it. Let's think about whether... Or actually, I'm probably going to start with the same place I have now. So I created this as prime, copied from a previous problem. In this case, I'm also using the sieve to calculate whether, or to help make this method a little faster. And then get the list of primes. So we know that 2 and 5 can never be part of this set, because any number that ends in 2 is divisible by 2, and any number that ends in 5 is divisible by 5. So we're going to exclude those and get this list of primes. Now I'm going to just start. So the approach that I was going for was a 5-level for loop nest, and I think that that might still work, but this limit needs to be a lot smaller. So, let's see. These are up to 3-digit numbers. Let's go ahead and for a limit of actually 1,000, so the highest prime is 1,000. I don't think this will work, but let's go ahead and try that first, just to see if we can prove out the algorithm for 4 steps. And what we're going to do is we're actually going to do something like this, where we have a lowest limit and a lowest set, and I'm also going to copy this part because it's just a print statement. Okay, so the way that I was approaching this was effectively for and then for I2 in range length of primes. Why am I not copying and pasting? Okay, so obviously this isn't quite what we want, because we want always to start at the previous index plus 1. Okay, so basic strategy here is we're going through every possible set, and we are going to figure out whether this set is a concatenating set. And if it is, then we'll check the lowest sum things. And actually, let's ignore I5 for now. Let's do this for just 4 levels. There's a better way of doing this, I'm sure, using recursion or whatever, but here's what we'll do for now. Okay, so what we want to do here is say if the concatenation of P1 and P2 in either order, if these two primes are a concatenating pair, we want to continue. And I actually have written a function for this called isConcatenating, and what it does is it converts both numbers to strings, concatenating them in either order, and then calculating whether those numbers are prime. So I'm going to go ahead and throw this here. And go ahead and use this is concatenating P1, P2. And if it is, then we go into I3, and we get P3 is equal to primes at I3. And if is concatenating P1, P3, and is concatenating P2, P3, we go into I4, and we get P4 equal to primes I4. And just continuing the pattern, if is concatenating P1, P4, and so P2 and P3. So we reach that, and we know this is a full concatenating set. So Now we say prime set equals P1, P2, P3, P4. This just makes life a little bit easier converting it to a list here. And then prime sum is just the sum of prime set. And then if prime sum is less than lowest sum, which I've started at limit to the power of limit, kind of an arbitrary number. Our limit is set to 1 million. So, it will be a very, very huge number at first. But if prime sum is lower, then we set our variable. Okay, so now let's go ahead and run this. So we have limited ourselves to less than 1,000 primes. So even with going through all of them this many times, this shouldn't take too long to run. Let's find out. It'll probably make a liar out of me. It'll probably take a while. Oh, it took 3 seconds. Oh, excellent. And that is the correct answer, we know, for size of 4, because that's what we just saw in our problem. It is 792.37.109.673. So, cool. Now we add our 5th layer and see how much longer it takes. Now, again, we're artificially limiting it to numbers below 1,000. We very well might not find something for all 5 doing it this way. But let's find out. So if it is all concatenating so far, we're going to do for I5 in range, I4 plus 1, length of primes, and then P5 is equal to primes at I5, and then we want to say if is concatenating P1, P5, and is concatenating P2, P5, etc. Then this line. All those over a bit. Except now we include P5. Everything else stays the same. Okay, so now let's think a little bit about optimization here, since I've already thought this through. What we're going to do here, if we get to this point, is we actually want to break out. Because let's say I1, or P1, the first prime that we're dealing with is 3. If we find an answer going through this way for starting with the number 3, that is going to be the lowest possible sum for the number 3, maybe. Ooh, maybe not. At the very least, we want to break out of this for loop, because the very last number will only ever go up. So it can't be that. That cannot be the highest number. So at the end of this, we'll just do a break. And that'll only cut out a bit, because it'll only cut out this last one increasing, but still, it'll be a little bit faster than without that. And again, I really think this is going to take a while. Okay. Exceeds the limit for integer string conversion. Interesting. That's very weird. 4,300 digits is too many. Oh, it never got reset. We never found the correct answer. So I'm just going to change this to limit times limit so that we don't have that. There we go. Okay, and that took 2 seconds to go through all of those. So, correct answer has to include a prime over 1,000. And just for reference, when I ran previously, I was able to find this set of 5 concatenating primes, and 2 of them are actually 6 digits. But this is the incorrect sum for the problem. I did plug that into Project Euler and it told me no. But let's go ahead and bump this to 10,000. It shouldn't make, or it will make a pretty massive difference, I think, in how quickly this runs, but let's see if it can get us to a correct answer. And like I said, this might take a while to run. This is like a 5 times nested for loop. That's almost never good practice. It creates an O of n to the 5th, which we probably don't want. It was just a way of doing it that I thought of. So it's just going through here, and we'll see if it gets to the correct answer within a couple of minutes. But quite obviously, this is not going to cut it. And we need something a little bit easier here. I had explored using iter tools to create combinations. However, creating combinations of the sufficient numbers of, or sufficiently high primes ended up being so hard on computation that my computer actually started to crash. Not fully, but I ended up restarting. So, not great for me. Not a great look. But yeah, this is clearly taking just too long, even with limiting it to primes of 4 digits or less. And even with that one break in there. The problem is that that one break might not be enough. Okay, so this is taking a bit too long. Okay, I'm gonna go back to assuming that 3 and 7 are part of this set, so I can reduce this. So, not that. We'll go ahead and start with 9, even though I know it is wrong. Actually, instead of calling that beginning pair, I'm just gonna say P1 equals 3 and P2 equals 7. Oh, we did find 5 concatenating primes. It did take much too long. That took 4 minutes instead of however long instead of under 1 minute, but I am curious whether this is the correct answer. If it is, then we'll still work on optimizing. If it is not, then there's something completely wrong with our strategy. Okay, so that is the correct answer. That is the answer that we want to get. So this thing that I was starting to do here, where I start with 3 and 7, wrong thing to do. Okay, so how can we go about making this easier on ourselves? How can we go about making this a little bit faster? Pretty obvious things come to mind. Like, we gotta find a way to not go quite this deep in the for loops, I think. Now, if we went ahead and started at 13, now that we know that that's the actual correct answer, how long does that take? My guess is that could take under a minute, but I'm not certain because of how it has to go through every single one of these. And actually, there is another way we can shorten this a little bit, even without doing this part. Which is to basically check at each point whether the sum is greater than our lowest sum. And if it is, then we break the loop. I'm going to start doing that here at P3. So, what I'm basically saying here is if we are at a point... Let's think about this only for P5 for a second. And then we want to say if prime sum is greater than lowest sum, break, because P5 will only get larger, so the sum will only get larger. And I'm going to say greater than or equal to, actually, because I'm assuming that I think that it won't come to the lowest sum again and have it be a different set of primes. So it could just be greater than, and then I can do the lowest sum reset if everything's concatenating. I'll do that. And again, like, right now I am trying to make it so that this runs faster, which obviously it's taking even longer now that it's starting at 13 somehow. So I don't know what's up with that. Starting at 13 is kind of cheating, so let's go back to our 3, 7. And then what we want to do is prime sum equals sum of P1, P2, P3, P4. So we can say if prime sum greater than lowest sum, break. Because again, if with just 4 it's greater than the lowest sum, we're obviously going too deep. So now in here, same thing, just only including P3. So that should get us running a bit faster, but I don't know if it'll be fast enough to get all the way. Takes at most 2 arguments. That's easy to fix because I can just do that. There, now you're summing a list, so you're happy. I'm not sure how much this will shave off in terms of time, but we're looking at this might take another 4 minutes. We'll see, have to wait and see, kind of. But let's see. I feel like doing this part feels smart. But obviously a nested for loop that's this deep is wrong. It's not an elegant approach for sure. It almost makes sense to, instead of doing it this way, well, no, because the lowest sum is going to end up being the wrong answer, because we found the correct answer, and the correct answer is 313 and 5197 as the 2 smallest numbers. So we can't just have it be the smallest sum all the way along. Let's see. I do think it is the case that if we get here and we're breaking here, we should break all the way up to I1. I'm not 100% certain, especially since there's such a big gap between these 2 numbers and the correct answer. But it feels correct. Could be wrong, though. Could easily be wrong. It's obviously not the first one found because the first one found, as I said, starts with 3. Okay, so still took 3.5 minutes, but it did get the correct answer. Double checking, 296,033. Okay, so we got the correct answer, took 3.5 minutes-ish. How long did it take last time? Also about 3.5 minutes. So it's still, it feels like, let's see, how many primes are there? I'm gonna go ahead and not let this one run the whole way, but okay. 12,000 or 1,227 primes. Now that we have the correct idea, I wonder if using iter tools would in fact be helpful. So iter tools allows us to have this combinations method, which we can use to just find all of the combinations, which I was finding that it took way too long. But now we have a more reduced set, I think. So I'm going to go ahead and call this prime sets is equal to list version of combinations for primes of size 5. Printf found possible sets. And I am going to go ahead and comment out all of this code for a second, just to see how long this step takes. Because depending on how long that step takes, this might be the wrong way to do it entirely. So we're looking to see if it takes less than a minute. It's obviously taking more than a few seconds. Still kind of feels like this is the wrong approach. Yeah, so obviously this is taking quite a bit. Okay. I do want to let this run, but not forever. And yeah, this combinations method with numbers, this many numbers, does slow us down quite a bit. So I'm a little bit stuck here. I should have heard. Not very much that I can do other than let my wheels spin here. Okay, Visual Studio Code is not responding. That's okay. Let it. It's because of how much memory that number of combinations uses. Yeah, I just need a combination calculator. Number of items, 1,227. Let's just say order is important, which is permutations, not combinations. Okay, so we don't really want the list of solutions, we want the number. Oh good, number is NaN. That's not a very well programmed calculator then, is it? Okay. When we're starting with a number over 1,000 is going to be a quite large number. So recording is the one. So I'm gonna say keep waiting. Try a different combination calculator. Not this one. This one's not good enough. 1,227. Yeah, so see how many combinations? That's a really big number. And that's why we're not able to figure out what they are using this combinations thing. So let's see if we can get that to cancel out. So what I don't want is I don't want to build in some sort of hard-coded, haha, I know it's this thing. Let's get rid of this. Not helpful today. Okay. So, what is a better way of doing this? I'm gonna try adding some more break statements, because like I said, I have a feeling like I'm not sure, but I have this feeling we can't keep going back. The same thing. Okay, I did say to close or to... I gave it the keyboard interrupt, but it does not like me right now. For obvious reasons. That's not what I wanted that, it turns out. And again, like, this is just sort of to see if we can make this cooperate. Okay, so now we have it so that we are assuming that for every I1, the very first set of 5 we find is going to be the smallest sum possible for that prime. I don't know if that's accurate. I have a feeling it might not be. But let's go with this just to kind of see. Let me just... hard time kill my Python program here. Oh. There we go. Oh, and I am zoomed in uncomfortably. Cool. Okay, so here again, I am hoping we can get it down to at least under 3.5 minutes. Like significantly under, let's say under 3 minutes. If not, then we need to come up with a whole new approach. Oh, okay, so that was under 1 minute. But it didn't find the things because it broke too early. Okay. So. It makes sense to have it here. I think. Because if it's the last 2... well, maybe not. We definitely need it there. Okay, so we've tried this before, and it takes too long. I'm thinking... There's gotta be some better way of breaking out of this early that doesn't involve, like, hard coding what we know the correct answer is. Okay, so what I'm gonna do here is, instead of range length of primes, I am going to go ahead and do range of 10. And that should at least reduce our running speed dramatically. And 13 is, let's see, 3, not counting 5, so 3, 7, 9, 11, 13. So it's the 5th one. I'm going to go ahead and say range of 5. This is cheating. I am basically hard coding in that I know that this starts with 13. But realistically, I'm saying if it starts with 13 or less. Let's see. Okay. So that got the correct answer, and it got the correct answer in 3 seconds. So if I up this to range 10, how long does it take to run? Okay, still a few seconds, nowhere near a minute. I'm gonna call that good. It's a little bit cheaty because we recognize that the first number in this set is going to be very small. But also it works. And it works in the amount of time that we need. And actually, I bet I can take this all the way up to 100 without it breaking our minute limit. Let's find out. I'm probably wrong. 100 is probably too much. That's a factor of 10. But let's find out. Okay. 35 seconds? Not bad. I like that better. I'm not going to up this anymore. And so I'm just kind of assuming that I built in some assumptions just to make it reduce the set so that it'll take less time to run. I still feel like 5 levels of for loops is probably not the most elegant solution to this. So if you've come up with something that is better, please leave a comment and let me know. I'm going to go ahead and not commit both of these files. I'm going to just use this one. But yeah, that's it for today, and I'll catch you in the next.